here's the book we're working on, Quantum Theory for Chemical Applications. And so I have basically the book open here in front of me, obviously, and also my Remarkable down here. And it's a little awkward to work with, but because of the microphone, I should maybe move the microphone to the other side. That could be helpful since I'm right-handed. Um, the microphone is on the right side because my work laptop is on the left side. So I don't know. Anyway, we're kind of dealing with it, and it's going okay. So last time we were talking about how if you have an orthogonal real matrix, it's a matrix transpose. This AT here is equivalent to its inverse. So by orthogonal, this is the definition of orthogonal, basically, right here. So if you can generate that, then you have an orthogonal matrix. Okay, so because of the definition of the matrix product, this means A is composed of column vectors that are mutually orthogonal and normalized. This is where the name comes from. The definition because of A, so A transpose equals A, implies that the matrix is at the same time also composed of orthogonal and normalized row vectors. Okay, so they put an example in here. So let's write this example down because I think we want to. 1 root 3, 1 root 3, 1 root 3, half minus 1. Oh, this is actually square root of 2. Square root of 2, 0. 1 over square root of 6. Sorry, my roots are getting kind of lazy at the end there. By taking the scalar products of the column or row vectors in this matrix, you can convince yourself that they are orthogonal and normalized. Orthogonal 2 by 2 matrices are parametrized. Guess we could convince ourselves of this, but I'm going to trust that that's true. Okay. Okay, so orthogonal 2 by 2 matrices are parameterized via this function for an arbitrary. Sorry, let me write a little bit more here because I think that maybe this is confusing. Okay, so let's see here. So taking products scalar products of rows or columns vectors in this matrix, you can see they are orthonormal. I don't know, maybe we should just do that. What is the drawing tab? So this is a program called RMView, and you can search it up on GitHub. I can go find it if you need to. And this is a Remarkable. So it's got, a pen that you can like write with and do that. And you can also erase, which is really nice. So luckily I have good enough handwriting that this works. Let's actually just prove to ourselves that these things are orthonormal because I want to real quick. I don't think it would be terribly difficult. I just need to get organized. Okay, so let's do that. Okay. So we're on J, which is going to be a tensor. J is going to be a two-dimensional tensor of floats for now. And we're going to have basically 3 row vectors. And we're going to have... Oh, I have it literally in front of my face. Okay. So is square root just a thing that I can do? Okay. So we can use we want the prelude square root. So 1 over... Oh, I don't think that we can do this, but we'll see. Square root 2. Okay. Okay. So, and then like that. And then what does this thing take in? A floating. Okay. So this can just be like float to float. That's probably fine. Okay, so started with Haskell recently. That's cool. And reading Haskell programming from first principles seems like an interesting language. Yeah, I would 100% agree. It's my favorite language. Let's move this here, I guess, so that we can see like the different vectors. I would say Haskell's my favorite language at the moment. I haven't found one that intrigues my interest as much, so... Okay, so 1 over square root of 3. This one's going to be minus 1 over square root 2. And then 1 over square root of 6. Okay, so this should compile now. Okay, now we need to basically take the scalar product of each of these vectors. So I actually don't know how to do this yet because like basically I need to get the first row and then like the second row, and I don't know how to do that just yet. So let's see if we can find that in the docs. For the quantum theory part, we're using a book, QTCA, Quantum Theory for Chemical Applications. It's a book by my PhD advisor. This is all random stuff, but we don't care about that. What's in here? All right. Unsure how to do this, so let's go back and just start. S vector. Rows. Index. Get. Insert index select index. What does this do? Doesn't say. All the good stuff is in here. So actually I wonder if we could just like instead of importing torch, just import torch functional. And then maybe torch tensor. Does this still work? Cool. So this might be a better setup for us because we don't really need the kinds of stuff that comes from Torch. We really need the stuff that comes from this library here, or this thing. Neat. So there's eigenvalues, SVD decomposition, Cholesky solver. Yeah, this is great actually. Okay. So what we need to do is figure out how to index a tensor with like, or just like get a row. That's the idea. It's probably at the top. Yeah, so we've seen these before. Is upper mean sum all? Maybe this isn't here. Or maybe I just need to do this in a different way. Earth. I'm not really sure. If anyone has any suggestions for what functions I can use, let me know. But, oh, take. Returns, what's take do? Returns a new tensors with the elements of input at given indices. The input tensor is treated as if it were viewed as a 1D tensor. What does that mean? If I take index 0, let's look at the PyTorch docs, I guess, and see what take does. So we really need 1, 9, and we're looking for a take. O 2 5. 0, 2, 3, 4, 5. Okay, so that's not taking That's not really the thing that we're looking for. Don't really need this. The squeezes do. I'm not sure how you take like rows out of these things. Can I do like a search like this in here? I think it would be like int to tensor to tensor. Is that a thing? Doesn't look like that's a thing. So I think that we can't really do what we're doing here. So that's fine. We can fix this. So let's just move some of this stuff out. So we're gonna have J, K. It's gonna be this. And then we're gonna have L is gonna be this one. And this won't match the type because it's one-dimensional. So there we go. And there we go. Okay, so we can just take reload this and take, I think, just we need the scalar product. So dot. Right? Dot J with K. Dot K with L. Right? So these are all the column, or sorry, the rows. And then we also want the columns. So we need 3, 3, and 3. Let's just grab this. So these are the rows, right? So we just now need the columns. So it's 3, 3, like so. And then 2, -2. Oops. And 0. And then O is 6, 6, 2 over 6. 6. There we go. Okay. So if we reload again, and then we do dot mn. I did something wrong. mnn. 1, 3, 3, 3. 2, -2, 0. Well, maybe it's infinity. Interesting. The scalar product's a dot product, yeah? Hmm. I'm a little confused at why I'm getting infinity from this. And it looks to me like I've done it right. 3, 3, 3. That's this one. 2, negative 2, 0. Oh. It's just 0. It's not 1 over 0. I by definition, that won't work. Okay, so now we should be able to do dot mn dot mo and dot no. Whoops. Okay, cool. So bug. I did that. My bad. There we go. So these are the rows in all right, let's do J, K, L are row vectors in a orthogonal 3 by 3 matrix. M, N, O if you take the scalar product between weird. So I noticed this yesterday that my sub and follower number are completely broken on this the website that deals with my overlay. I guess I need to email them or something. Yeah. Any of the row columns with each other, you will get 0. Same is true for the column vectors. I wrote row columns. Okay, so if you take the scalar product, dot in Hasktorch. Okay, so if you take the scalar product dot and Hasktorch between any of the row vectors with each other, you'll get 0. Actually, did I check that dot m with itself is 1? So if you take any of these with themselves, they also need to be 1. Okay, so we're doing good. So that's the normalized part. This is orthogonality. Normalized means that if cool. So orthogonal, normalized, orthonormal. Cool? Cool. Okay, so we've proved it. Just wanted to do that because it's been a while and I think it's important to understand. Okay. Does anybody have any questions so far? Okay, so An orthogonal 2x2 matrix are parameterized via this thing here. So orthogonal 2x2 matrix parameterized by okay. The column vectors are normalized because of cosine squared alpha plus cosine squared alpha plus sine squared alpha equals 1. Later, we see that these matrices describe rotations of a 2D vector by an angle alpha. In case of complex matrices, the transpose of A in equation B3, which is the one that states that for an orthogonal matrix, the transpose is equal to the matrix inverse. Hey, Freezy. No? No what? No math? No. No what? Okay, so can be replaced by the Hermitian transpose. A matrix U is called unitary if it has the following property. So this is U dagger U equals U dagger equals 1. Oh, you don't have questions. Okay, I got you. No questions. Good. Which means or implies that U dagger. Oh, I was thinking about a different symbol for dagger. Let's see. Let's try it. So right now, this is what I'm writing. Like I'm trying to write. Let me write it in a bigger shape. I'm trying to write the following, like something like this for a dagger. But what if instead we went like that and called that a dagger? Because it doesn't look like a plus sign anymore. So I feel like that's probably a better way to do it, and it'll also be easier to draw. So here's the difference. So like that's kind of hard for me to draw. That's not so bad. So I think we're going to call that a dagger because it's a little easier for me to draw. Okay. All right. So for the same reason that a real symmetric matrix is Hermitian, an orthogonal matrix is also a unitary matrix. In other words, we may use the words unitary Hermitian versus orthogonal symmetric interchangeably if a matrix with these properties is real. For the transpose or Hermitian transpose of a matrix product, the following rule is readily established. Okay, so A, B, dagger is equal to B, dagger, A, dagger. I like that dagger, actually. I think it's pretty good. Or it's, like, good enough. Okay, so I think that this rule is very useful. All right, so section B3, determinants. These are weird. I haven't thought about determinants in a while, and they're pretty strange. Okay, so a determinant is an important property of a matrix that is useful in particular when calculating the inverse of a matrix or when solving linear equation systems. For example, the inverse of a square matrix is only defined if the determinant is not 0. Okay, so a determinant of a square matrix. Wait, sorry. Let me rewrite this. So, take a square matrix. A to the negative 1 is only defined when determinant A is not 0. Okay. Okay. I'm not even going to say it. So the determinant allows one to determine whether a homogeneous linear equation system has non-trivial solutions as well, apparently. So you can write the following: determinant A or A like that. I think I've seen this quite a bit. You should be able to see my red little marker there. I've seen that written a lot. Okay. Yeah, this is not the absolute value. Okay. This is a pretty weird looking equation, so be prepared. So we have sum p minus 1 to the p power a1 p1 a2 p2 an pn. A very strange equation indeed. I'm not gonna like read this whole thing, and we're just gonna like go to an example because it's probably a lot easier to understand if you just look at an example. So here we go. 1, 2, 3, and 4. So the way a determinant works is you start with the diagonal product. So if we take the determinant of this matrix, we start with the diagonal product. That's the diagonal. So we just take 1.4. Okay. So this corresponds to the columns. So if we call these the columns P1, and actually let me move this down a little bit because I don't want it to interfere with that equation there. So do that again. So 1, 2, 3, 4. This is column P1, column P2. And so if we take 1 and 4, this is like P1, P2. Okay. Okay. Sorry. So if we how do I say this? So this is basically column 1 and column 2, okay? So we need to take permutations of the columns. And basically if you I don't know how to say this. It's such a weird equation. So this is column 1 and 2, the permutations. So it's like we start in row Z, like the first row here, and we take 1. That's the column 1. Then we go to the second row and we pick column 2. Okay, we're always going to go from top to bottom down the matrix. So 1 and 2 means 1 from row 1 and 2 from row 2. So the only other permutation for this is 2, 1, okay? Which means that we're going to take 2 from the first row and then 3 from the second row, okay? And then we just like add these things together. That's a horrible syntax, but let's just write 1, 4 like that. We don't add, we multiply. Sorry. Okay. Now, this one is called odd. And the reason it's odd is that there's one interchange between indices. So that means you have to preface it with a -1. So this will have a minus sign out in front, and then we just take the numbers at those column locations. So 2, 3, 2 times 3, and then the determinant is minus 2, I guess. Right? So that's how you calculate a determinant, which is like incredibly weird for what it's worth. So let's do a bigger example, and then maybe we can hopefully like actually Haskell can help us with this, which is kind of cool. I think it can anyway. Let's look. So if we have a 3x3 matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9, and we want to compute its determinant, we'll start with the diagonal, which is going to be 1, 2, 3, right? So 1, 2, 3 means 1, 2, 3, and we just multiply these things together. So 1 times 5 times 9. That's the first entry. And then we need to get all the permutations of this thing. So I think that Haskell will do this for us if we just use a function called like permutations. And that's in data list. So if we import data list permutations, and then we run permutations on the list 1, 2, 3, we'll get all the permutations of this thing. So there's 6 of them. Okay. And then from here, we can just start like taking these things and grabbing the values. So we've already done 1, 2, 3. So actually, let me just move this down because it's going to be easier to do this. So we have 1, 2, 3, and that one is what we just did. 1 times 5 times 9. And then the next one is 2, 1, 3, 2, 1, 3. So this one's odd because we have one index switch. So this one's going to be a negative. And then we just go through and we grab the things. So 2 is 2. 1 is 4. 3 is 9. Okay? And then we just keep going. I'm not going to do all of them, but hopefully that's enough. If you have any questions, like, feel free to ask. I feel like matrix determinants are kind of strange. So if we want to do this in Haskell, we can start with the 1, 2, 3, 4 matrix and just see if we get the right answer. OP. And we need a 2x2 with 1, 2, 3, 4, like that. And then we can reload this thing, and we will run determinant of P. And there you go, -2. So we also already have, where's that one? I think it's not that one. This one, G, which is the 1, 2, 3, 4, 5, 6, 7, blah, blah, blah. And so if we run the determinant on G, there we go, its determinant is 0. And that means its inverse doesn't exist. So, again, so let's just call this A. Yep, and if we take this, then we get 0, which means A to the -1 doesn't exist. And if we try to run the matrix inverse, by the way, inverse G, it literally crashes, and it'll say up here somewhere, U of 3, 3 is 0. And I'm guessing that U in this case means the determinant or something. So you can't do it. So that's kind of cool. Man, these bots are all over the place. Go away. Okay, so determinants. And I was thinking about writing determinants in like Haskell land because you get this permutations thing, which is pretty nice, but I still actually don't know how to like pick out entries from the matrix. So I'll just leave that to a library to handle. Okay. This a little bit and move this a little bit. Okay, so there are algorithms by which to reduce the calculation of a determinant to order n to a sum over determinants of order n minus 1. The theorems can be implied until one has reduced da 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 da. There are a number of important rules for calculations with determinants. So some rules. So determinant. Well, let's just write it like that. So 1. The determinant of A transpose is equal to the determinant of A. If a row or column of A is multiplied with a factor lambda, then the determinant is lambda determinant A. I don't know how to write that in like a terse notation. So we won't try. So I'm not exactly sure why that's useful, but like why the rule is useful, but I could see why that works. Okay, so if two rows or columns of a matrix are interchanged, then the determinant changes sign. Okay. From rule 3, it follows that if two rows or columns of a matrix are equal, then its determinant is 0. If okay. The determinant of a matrix does not change if one adds to one column or row a multiple of another column or row. The determinant of a matrix does not change if one adds to one column a multiple of another column. Okay. I feel like these are getting kind of strange. Okay, so from rule 5, it follows that if two columns are equal, one can subtract the two and create a column with all entries being 0, because every term in the determinant must contain a factor from this column. This again shows the determinant is 0 when two columns are the same. The determinant of the inverse of a matrix is... Oh, this one's kind of interesting. The other ones are like kind of wordy to me. I'm not sure how to write them in a terse syntax, so I'm not going to. So the determinant of an inverse is 1 over the determinant of itself. That's kind of cool. Which is why oops. That's cool. Okay. The determinant of the product of two matrices is the product of their determinants. So determinant A B is equal to A B. Cool. Okay, so it says the determinant of a diagonal matrix is the product of its trace. So the determinant of a diagonal matrix is equal to its trace. Is that hopefully that's clear? And so it says this is one possible way of calculating determinant by diagonalizing the matrix. So if we can diagonalize the A, then its trace is just its determinant. Okay, so the determinant of a triangular matrix is the product of its diagonal elements. Oh, it's the product, not the trace. That's the sum. Doesn't its product have a name? I don't think so. There's probably a name for that. I just don't remember what it is. If somebody remembers, let me know. Okay, so determinant of a triangular matrix is the product of its diagonal elements. This is another way to calculate a determinant. One applies rules 3 and 5 repeatedly to bring the matrix to triangular form. Okay, so these are just like algorithms for that. Okay, so that was kind of interesting. A linear equation is a number of unknowns x, y, and z. Okay, so linear equation something like this, where A, B, C, and P are numbers. The numbers A, B, C on the left-hand side are called coefficients of x, y, and z. The term linear is used because no higher powers of x, y, and z occur. Okay, so A, B, and C are coefficients to x, y, z. No higher powers of x, y, z make the equation linear. Not surprising. So here's an example. 3x minus 2y plus 5z equals minus 4. A solution to this equation is any triple of numbers x, y, and z for which the equation is satisfied. More generally, we may have a number of equations, say n, for a number m of variables. M may exceed the number of characters in the alphabet. Therefore, it's convenient to number them the form x1, x2, x3, etc. Likewise, we can label the coefficients. In the first equation, okay, second equation, so on the constants on the right-hand side of each equation, da-da-da-da-da. Okay, so by doing so, we can collect all the coefficients in a matrix A, all the numbers on the right-hand side in a vector B, and write the whole system of linear equations in the compact form. So A, X equals B. Here, the unknowns x1, x2, x3 are collected in the vector x. So it would be, like in this case, it's x, y, z, I guess. Okay, so if we write the columns, so x1, this is like the x's, and then if we write the columns of A as column vectors, okay, which interprets the matrix vector product. Sorry, there's a lot of reading here. I'm just trying to like distill it. From which okay, so in this case we would have like a matrix, but it would be just 3, 2, 5, I guess, in the columns. I'm a little confused at what would be on the right side, though, if this is supposed to be a vector. Okay, cool. So let's rewrite this a little bit. I'm going to skip this because the actual solution is kind of weird. So we can also write this x1, a1, x2, a2, xm, an equals b, which interprets the matrix vector product of equation in the alternative form of b being a linear combination of vectors a sub I. Okay, so these are all vectors. Let me just like use the physics notation to like make it more obvious. So these are coefficients. These are vectors for an equation of a vector of coefficients. What is this thing? Sorry, I'm having a hard time reading this. Okay, so the equation has a solution only if B can be written as a linear combination of the column vectors in the coefficient matrix A. In the case when not all b sub I are 0, this statement is equivalent. Oh, these are like all the solutions. I see what's going on, I think. This statement is equivalent to the requirement that the determinant of A is not equal to 0. In this case, A can at least formally be inverted. We can get rid of the matrix A in front of the unknown vector x in equation B7 by multiplying both sides of the equation from the left with the inverse of A. Therefore, the formal solution of a linear equation system x is equal to A inverse A x equals A inverse B. In practice, the computation of the inverse A and calculation of the solution to the equation system by explicitly calculating the matrix vector product A negative 1B is rarely used because there are much better and numerically more stable algorithms available. Cool. Okay, another way of interpreting the meaning of equation B7, sorry, I should keep writing this, AX, equation B7, is in the sense of the transformation of vector x into B and asking the question, given the vector B of the transformation together with the transformation matrix A, what was their original vector? A special case is the homogeneous linear equation system for which B equals 0. Okay, so this is called homogeneous linear equation system. Yeah, I guess it's really not. Kind of a note. Interesting. Okay, so obviously x equals 0 solves any homogeneous linear equation system. This is so obvious that x equals 0 is called the trivial solution. A homogeneous linear equation system. Okay, so only has solutions other than the trivial one if the determinant of A is equal to 0. Okay, so it says, based on the rules of determinants, there are infinitely many ways to create a 0 column in A, and therefore the equation system has infinitely many solutions when the determinant of A equals 0. Linear equation systems are solved by the so-called Gauss-Jordan algorithm. Basically, any operation that leaves the determinant of a matrix unchanged. Okay, so one attempts to add multiple of rows to other rows to bring the matrix to triangular form. When the equation system is in that form, one can immediately calculate the solution by back substitution. For a 2x2 problem, we just used the we used the following procedure. Write down the two equations explicitly, eliminate one of the variables in the equation by substituting the other equation, and solve this equation. Okay, so let's start from the top here. All right, so we have A and X. Sorry, that was a lot of talking. I mean, this is like a book about math, so it's going to be talking. Like I can't avoid that. 1, 2, 7 minus 9 times x1, x2 is equal to 4. Sorry, not that. Not 4 over 2. 4 and 2 b, right? So vector, vector, matrix, good to go. So this is a linear equation system, x1 times 1 plus 7x2. So you can see like matrix equals 4. Right? And that's basically the matrix product, right? Because it's just this and this gives you that. So the other one is minus 2x1 plus, sorry, minus 9. Minus 9x2 equals 2. Okay, so solving the second one for x1. Okay, and then substitute this into there. So multiply the whole thing by 2. And then you can just do some trivial math, I guess, to find out that x2 is equal to 2. And then x1 equal to minus 10. And obviously that's your x1 and x2 up there. X equals 2 minus 10. And how do we know that this is the inverse? I guess you would have to calculate it. I wonder if we can actually get that really easily from PyTorch. Let's see if it'll actually compute this one. I'm curious if it will. Okay. Sorry, I was like looking down the whole time. It's gonna be hard to get my attention. Joker, out of curiosity, I saw the implementation of permutations function in Haskell, and I was blown away. Yeah, it's a pretty complicated solution for the problem, but like because you mentioned earlier that you're like getting started with Haskell, so the recursion is going to feel really awkward at first, but you'll hopefully start to feel like it easier. It gets easier as you do it more. Okay, so next time we are going to compute inverse of A in linear equation system with Hasktorch. We are going to try to solve the linear system AX equals B in Hasktorch. And we will continue. Whoops. What are we at? I think this is B.4. Yeah. No, we're actually move on to eigenvalues, eigenvectors, and functions of matrices.